How's everybody doing today? Good? Thumbs up, thumbs down? Good. All right. This is really cool. I've never given a talk to everyone with headphones on, but I figure if I'm bombing, we could just like play Darude Sandstorm and everyone could just like fist pump for 20 minutes straight, and we can just do that. All right, so let's talk about Roller Coaster Tycoon. Well, first let's talk about, I work at Shyp. If you want to send anything, we'll come pick it up from you, package it, find the cheapest price out of UPS and FedEx and the post office, and then send it out. And we have iPhone and Android apps if you check us out in the App Store. So this project started when I was 12 years old. I played a lot of Roller Coaster Tycoon. How many of you have played Roller Coaster Tycoon? Wow, a lot of people. All right. If you haven't, it's an amusement park game. You can build roller coasters and people ride them. So when I was 12, I thought, well, it's fun to build roller coasters, but what if I could build these with a computer program, right? Like, what if I could tell a computer to generate cool-looking roller coasters for me? Wouldn't that be cool? When I was 12, I didn't have the capability to do this, but now I do. So I started working on this about 2 years ago. Just a project to try to build cool-looking roller coasters from a computer program. That's kind of the goal, and then how do we even approach that problem? How do we start defining things and figuring out what our strategy is going to be? There are some nice things about Roller Coaster Tycoon that make this problem kind of tractable, right? So there's a grid layout. Track pieces sort of like intersect at the four corners, or the four straight edges of the grid. There's a defined number of track pieces, like we're not drawing like Bezier curves to get from point A to point B. So that sort of limits the branching factor and sort of makes you think that if you can just load the track pieces, you can probably try to build an algorithm or build something good. What is a cool coaster? So this is the coaster my program made. Thanks very much, and I'll see you guys. Any questions? That's not true. I didn't actually build this one. A lot less cool, the ones that I built, than this one. But yeah, so what is a cool coaster, right? Like, we can look at this and it looks cool, right? But what does that even mean, right? Like, we have to tell the computer what cool means so it can sort of generate that, right? Or figure out whether it's making progress towards cool or not cool. The game gives you these kind of ratings. When you build a coaster, it sends a car around, and then when it completes a loop, it computes all this information, right? It computes sort of the excitement and the intensity and the nausea ratings, and then people will like your coaster or not like it. If it has high excitement and low nausea, they'll like it a lot. If it has too high of nausea, people will be like, that thing will make me sick, and they'll make a green face on the screen. So we can use this, right? This is good enough for our purposes. If we can figure out how to compute excitement and intensity and nausea, we can use those ratings as the basis for what is cool and what is not cool, right? We don't know how to generate those yet, but if we can, you know, something is generating these numbers. If we can reproduce that process, then we can make a cool coaster. All right, how do you interface with the game, right? This is the next thing, is like, how do you actually like put the coasters into the game, right? Or how do you generate those excitement things? There's a long history of kind of fun projects along these lines. This is a Super Mario player, and you can see up in the top left corner, they're actually parsing the screen, right? And they're like generating blocks and generating the bogeys as they're going, and then they're simulating key presses in the game. This is a lot more sort of intense than I wanted to do. I didn't want to have to be like parsing the screen or simulating like mouse clicks or key presses or anything. Here's another fun one. This is someone playing Duck Hunt, and they actually had a camera focused on the TV that was sort of finding the ducks, and then that was showing the rifle where to aim to point to kind of shoot it. This is way more complicated than I wanted to do, mostly because I was on vacation. So I was looking for something simpler than this. So Roller Coaster Tycoon stores track data separately from the game. This is me running Wine on my Mac. Wine is a Windows emulator running on my Mac, and you can see there's all these kind of track files. And it's really funny, if you look at the last modified times on all the track files, it's from like 1999 when this game came out. So if we can figure out how to read this track file, then we can probably just write straight to that track file and then load that in the game and kind of sidestep all of the mouse clicking and visual screen parsing that we'd have to do in the previous screenshots. So you try to open up the TD6 file format and it looks like garbage, and then you go and read online about the file format. This is a guy named James Hughes, who's kind of like the first person to decompile the game, and he put up this website called Tycoon Technical Depot. It was really fun kind of doing the research and sort of figuring out this project and sort of exploring this project, because you kind of like step into a web time machine back to like the GeoCities days. Like this page was modified in 2003, and most of the like forums and stuff are from that same era. So it's pretty neat. They load really fast too. Pages load really fast. There's no JavaScript frameworks or anything. So yeah, so this explains the TD6 file format. The biggest ride you can have is 37 kilobytes, which in 1999 was massive. So they invented this kind of run length encoding compression format. That's not like gzip or anything. It's custom. And that's how they kind of like compress the data before they store it on disk. So this is the basic encoding format. We read a byte. If that byte is negative, read the next byte and then copy it that many times. So if we got like negative 17, read the next byte and then copy that one 17 times, right? And then that's your decompressed file, right? If the first number you read is bigger than 0, copy that many bytes, and they're probably unique, right? So if you get 10, copy the next 10 bytes. They're unique. Just copy that. So Go has interfaces. Read and write are sort of implemented by all kinds of different applications and protocols. So if you can have your encoder or decoder conform to this interface, you can kind of like decode and encode straight to any kind of data stream, like a file or HTTP request or an HTTP upload or any kind of thing. This is really nice, right? I didn't have to do a lot of work. You just encode those 3 steps in the read, and then you encode the reverse of those 3 steps in the write, and then Go will just repeatedly call those functions until the whole file has finished reading. So yeah, so that was pretty neat and easy to do. So okay, so we have a plan of action now. We're going to generate tracks outside of the game, save to this TD6 file format, then load them in the game, and then kind of iterate, right? So we can load them in the game and say, well, this is good, this is bad, this is not correct, and keep going from there. Okay, how to represent the track pieces. I didn't want to have to do this manually, right? There are a lot of track pieces in the game. I also wanted to see how the game itself represented the track data. For things like, there are things you need to know about a track, right? How many spaces does it go forward, right? How many spaces does it change in elevation up or down, right? Does it turn to the left? Does it turn to the right? All this sort of stuff you need to know about the piece to be able to like generate a track and like figure out whether the track is a complete loop and all this sort of stuff, right? So how do you figure this out? The problem is the game itself is written in x86. It was written by one guy, an x86 assembler. So it's kind of forbidding to look at it and figure out what's going on. Just really fast, what is x86 assembler? So when you write a program, this is like kind of like pseudo Python. Your CPU, like your laptop, doesn't actually know how to like parse this and run it natively. It kind of has to get compiled down into this other language called assembler, which I'll show you on the next slide. This can happen either when you do a compile, right? Like for C or Go, you compile machine instructions. For languages like Python, they're maybe interpreting it and generating those instructions on the fly as your code is executing. And maybe generating different ones as it goes along if you have something like JavaScript or just-in-time compiler. But yeah, so here we have this like really, really dumb sample program, and let's see what machine instructions this might generate. So yeah, so this is what this might generate, right? So CPUs, your computer has somewhere around 10 to 30 registers on it. A register is for 64 bits. And well, it's 64-bit, right? A 64-bit CPU is 64 bits in each register. And basically, we load a bunch of data into those registers, and then we operate on it, and then we save it off to the hard drive or to memory. But the CPU, all the like action is happening sort of in the CPU in these same registers, right? So here on line 1, we're moving the value 3. $3 is like the constant 3 into the register CX, just the name of the register. And then we're adding 4 to it, right? So add 4 CX as, add 4 to this value and then store it in the same register, right? B equals 6, we're moving the value 6 into AX. Then we're comparing. So CMP is compare. What this does is this checks the two values. If CX is bigger than AX, it will set a bit in what's called the flags register, right? There are 64 flags that you can set. One of them is the less than or equal to flag. It will set that bit, and then the next line, JLE, stands for jump less than or equal to. It checks that bit. If that bit is 1, it will do the jump. If that bit is 0, it will not do the jump, right? So if that bit is 1, we'll jump to line 9. You can see there's a label for line 9, where we increment B, right? If that bit is 0, we just fall straight through to the next line where we're incrementing CX instead, right? So this is how you kind of do control flow. This is really, really, really basic x86. There are a million x86 instructions. But the whole game is written in sort of this code, and I'll show you more examples as we go along. So there's a lot of instructions in the game, 4.8 million instructions, 1.2 million bytes of data. That's stuff like the tracks and stuff like the price of a hamburger and all the other stuff that kind of happens in the game. Sometimes when you compile from a high-level language, you get symbols like, here's the start of a function, right? Or here's this thing, right? You get sort of more sort of helpful information. This has none of that. It's just the instructions. And the other thing is you don't have really nice sort of program flow, right? Like when you write in a high-level language, you get if statements and for loops, and you're kind of constrained in like where you can jump around in the program. There's a lot of sort of go-tos and a lot of weird sort of control flow statements in the program just because it's x86 and you can do like whatever you want. So it's hard to read from that perspective. So yeah, how do you find what you're looking for, right? Starting at line 0 and reading through 4.8 million instructions is not going to be feasible. So I was kind of fortunate around the same time that I was looking at this project, literally within the same week, a guy named Ted Johns started this much, much more ambitious project, which was to decompile the entire x86 code into C, right? That is, generate the equivalent C functions for every single line of x86 in the game. This is called OpenRCT2. It's really cool, and like I started this 2 years ago, and they have made a ton of progress. Like none of this existed 2 years ago. But yeah, just like a ton of really cool stuff that they've done in the game. So the first thing is the game itself is really, really, really specific to Windows. This is why they never released like Roller Coaster Tycoon 1 or Roller Coaster Tycoon 2 for Mac or Linux, because it was just like super Windows specific, and the whole thing was in x86. So there was no way to generate like a Mac or Linux version of the game besides like rewriting the whole thing. Roller Coaster Tycoon 3 was a complete rewrite. That's why it is available on every platform. But if you decompile it into C, when the C compiles, it knows how to generate all of those instructions for each of the languages that you're running on, right? It knows how to listen for keyboard input, for example, right? Or draw things to the screen on each of these different languages, right? And how to like generate those commands. A lot of that's handled via this library called SDL2, which is a drawing library that works on every platform, right? So once we have it in C, you can run it natively on Mac and Linux and get big performance boosts out of that. The AI in the game is not very good. There are things like people will try to go to a ride and they'll get confused about how to get there because they can't figure out the pathfinding. But yeah, so people can fix this, right? If they understand the algorithm, which is now much easier to read in C, they can improve it, right? Or you can add in some sort of different algorithm if you want. There's a Twitch integration, which is like crazy. Like you can like, there's a Twitch button in the game, and you can like publish what channel you're publishing to and all this stuff. I haven't tried it. I don't use Twitch, but you can. More languages. I proposed janitor unionization, like the ability to have the janitor strike and like your park just gets really dirty. But no one else wanted that idea, so it's not in the game. Yeah, this is crazy. So this is Android, OpenRCT2 running on Android. I'm not sure how playable this is, but like someone did this. So yeah, so I mean they've really come far from like the days of 32-bit Windows using x86 instructions that were valid in 1999 to now running on a Java phone. So yeah, so this is a super neat project, openrct2.com. You can go check it out. But yeah, so this was kind of helpful for me when I was doing my thing. The one thing is you still need to buy the game, right? Like they didn't like redraw all the coasters and everything, and they didn't redraw the scenery. You still need to buy the game and like load in all the assets. just the engine's changing, right? So like how these coasters are moving around, and like let's add cheats, and let's add like you can go faster through the game and all this stuff. But you still need to buy it. Like don't skimp on buying it. Sorry, more things about OpenRCT2, and then I'll get back to how I found all this stuff. How do you test as you go, right? So they're decompiling 4.8 million instructions. You can't like decompile all of it and then try to run it and then say, oh, well, I screwed up this part and this part. It's going to be impossible, right? You kind of need to like do it incrementally. How do you do that, right? So when you specify like an EXE, there's this interface called the ABI, the Application Binary Interface, that says basically like start reading at this specific part in the binary, right? Like start reading at this instruction, and then go from there, right? So that's sort of the standard that every binary complies to. What they did was they compiled their C code and the game, right? The game EXE into one shared DLL. That modified the entry point for the game to point to their C code, right? So instead of loading the game's entry point, they loaded their own entry point. Now we're running C code, and so then what we can do from the C is we can actually like call into the x86 function, right? And then we distribute that new exe. Now everyone is running the C code, right? And so then we can kind of run the C code, and then as we need to, we can call into x86. The way that works is they have these functions called RCT2 call proc, RCT2 call thunk. And what these do, these will initialize the state of the world. You can see here it's setting a bunch of registers. And the first value there is an address. It's an address in the game, in the original game. So it's going to say jump to that address, load all these values into every register in the CPU, run that x86 subroutine, and that will do something, right? Like maybe it will draw something to the screen or change some value that we haven't decompiled into C yet. And then what happens is once that subroutine finishes running, it will return control back into the C code, right? So that way you can kind of test as you go, which you really need to do when you're taking on a project like this. Most of the game has been decompiled into C now, which is pretty cool. But for a long time, this was how they sort of worked around this, and incrementally compiled as they go. How are things? Thumbs up, thumbs down? Okay, great. So my plan was I need to find two pieces of information in the game. The first was the track data, all the stuff about the loop-de-loop is this high and goes this far forward. And then I needed to find how they were generating excitement and nausea ratings as they went. Much less ambitious than what they were doing, but also kind of orthogonal to it, at least it was 2 years ago. So the way you do this, you use this tool called IDA Pro. This is the like standard for reverse engineering x86. A lot of security people do this for like figuring out how a binary, if you have a binary, you can open up an IDA and figure out what it's doing. This is the tool that we were using to read the game and figure out what was going on in the game. It's pretty pricey, but if you're paid to go here, your company could probably cover it. So yeah, so you get output that looks like this. It kind of groups functions into contiguous blocks. And you get some nice stuff like if there's a jump, it will show you with a green arrow and a red arrow. This is what happens if the jump is successful. This is where you go. This is where you go if the jump is not successful. So you can kind of get a sense for how the program is running and what it's kind of doing as it's going along. So yeah, so it was a lot, like figuring out this information was a lot of just staring at this and trying to figure out what values were in each register and like what each piece of code that was completely unlabeled was trying to do, and then going from there. It was hard. It's kind of like code breaking in a sense because you just don't know anything, right? There are some tips, right? So as they were decompiling OpenRCT2, they were sort of keeping the x86 pointers and the C code side by side. So as they decompiled something into C, they'd point at, they'd say, this is the original instruction that this is the original subroutine that I just decompiled into C. For reference, right? Like if there's a bug in the C version, they can go back to the x86 version and look at it. This was also useful for me because then it was a jumping off point. I could see, oh, okay, this is how this code looks, right? Or this is how they handle rides, right? Or this is how this thing handles heights and various things, right? So I could kind of read the assembler code and see what it was doing, right? The parts of the code that I needed, unfortunately, like weren't decompiled. They were super, super buried deep in the game at the point that I was doing this. So I still needed to go read the x86 code, but yeah. So the other useful thing is the track data always shows up in the same order in the game. So anytime track data is referred to, this is the same technical depot site. It's always in this order. So first piece is always flat, right? The next 3 pieces are stations. The next one is 25 degrees up, right? Just like one length piece, but just 25 degrees up. So you can kind of use this, right? Like if you see a piece of data in the game, you know it's going to be in this order, right? Which helps you make guesses. So I figure I'm looking for something like this, right? There's going to be a pointer to some piece of data in the game that's going to point to like the first track piece, right? That track piece is going to have like some amount of, it's going to be like 10 bytes or 12 bytes or 20 bytes or however wide it is to store all of the data for that track piece. Multiplied by the track piece number, right? So 0 is flat, 5 is 25 degrees up. And then there's going to be some offset into that width, right? So let's say like the information about elevation is at offset 3, that's what I want to read, right? So this is the kind of formula for how I'm expecting the data to look in the file. It's not much to go on, but it's enough to start like making guesses about where stuff is as you kind of read stuff and come across addresses that look interesting, right? So this is the basic strategy. You just open up the exe, read at a specific point. This is really nice and go. You just like scan all of the data in the binary into a byte array in memory, starting at a specific address, right? So I would just like plug in different addresses and see what kind of data I would get. Then once you had all the data in memory, you'd kind of loop over this data and print it to the screen. And Go has really nice formatting tools, so you could like control the print and display and change from hex to int and Boolean and all kinds of different stuff really easily, right? And then I would print out like a guess. So this is a guess. This is me just loading data from the binary and then printing it out and sort of comparing it to each of the track pieces, right? So I'm looking for, could this be like the representation of height? Could this be the representation of left turns and right turns, or forward or back, right? As I'm going, right? So I'm kind of matching up the numbers that I see here to the track pieces. And yeah, so I just try this and keep trying this until I got sort of data that would make sense, until it matched up with all of the track pieces in the file. Then I'd say, okay, I found it. This is where that information lives, right? The other nice thing about printing it like this is you can tell right away whether your width is on or off, because if it's off, it'll just show up in diagonals, right? Like you can see the 255 in the right-hand column. It'll just be like kind of like in the each row you go down, it'll be like left one column. So then you can change your width until you get sort of data that is meaningful. Okay, so I'll spare you the like month where I didn't figure this out, but I eventually made a good guess, which was looking at like the strings in the game, right? And this is actually a really useful technique for any program you don't know that much about. If you're trying to figure out where something is just start with what gets printed to the screen and kind of work your way backwards from that, right? Like figure out where that string is with grep or something, and then figure out what code calls that string and what code calls that string, and then you kind of get a sense for where you are in the game. So in this case, I looked at the string too high, and I said, well, to generate this error message, you probably have to add something to, or like do a height comparison, right? And then if you're doing a height comparison, you need to know whether the track piece is, going up or down. So let's try to find this, right? Let's try to find where this piece of code is getting loaded in the game, where this error message is getting loaded in the game. In RCT2, everything is in hex, which is base 16. So just fire up a Python editor, type in hex 878, you get 36E. You punch this into IDA. There are a lot of there's a lot of sort of extraneous output here, but there are 3 really promising examples, right, where we're loading that 878 number into a variable. Here's one subroutine, right? We can go look at this. And then we see this really promising piece of code right near there, right? So we're comparing a value in a register to the number 2. Then we have JB, which is jump below. It says, if this is below this value, jump to this one place, right? And then immediately after that, if that's not true, we're comparing it to a pretty high value, 250, and we're saying, if it's above this, jump to this other place, right? Which is actually loading the too high string, right? So this looks really promising, right? And then what you do is you kind of back out and you look above and you keep tracing around. And you actually found the part where we're adding heights, right? And then I got the height data, and from there I got all the rest of the sort of track data out of there. Rating data. So how do you find rating data, right? This is a Cricket House. This is the simplest ride in the game, right? Every ride in the game generates excitement and nausea. It's going to be really complicated for a roller coaster, but it's going to be really simple for something like a Cricket House. So I was hoping for like just constant values for excitement and nausea, right? So you cleared out every scenery and hill and everything in the game. You build a Cricket House. You get the excitement and intensity and nausea. They're these values. I tried searching for these in the game. I get 0D7, right? Search for this. You find this really promising subroutine where we're loading these three values, if we remembered from the last slide, 215, 62, 34, into values in memory, and then we're returning from this function, right? So this is really, really promising, right? Like this is exactly the Cricket House, like this is an accident. You scroll up a bit, you see this sort of jump table that lines up to rides in the game, which you also know the order of the rides in the game. And you can kind of go inspect these functions and say, well, bumper boat shouldn't be that complicated, and the function is short, and a mine ride is more complicated, and the function's long, so this is probably where excitement and nausea get computed, right? Which is great. So now we have all this, we can figure out how excitement and nausea work. What is excitement? So how do they actually compute this in the game? They start with some constants. Steel roller coasters starts with a very exciting value. The length is the biggest determiner of how exciting the ride is going to be and the duration of the ride. You get really big pluses the longer the ride is. The max speed, if it's a really fast ride, you get a lot of excitement. If the max speed is too low, you get a penalty. The average speed, the number of drops. If the largest drop height is too short, you get a penalty. And you get subtracted off if it's too intense, right? Like if people are barfing, they're not having a good time. So you get a penalty for that. The other thing is, right, like max speed is great, but if we're going 100 miles an hour, we're probably not enjoying ourselves. And this is how they kind of deal with this in the game, is things like num drops and max speed affect the intensity more, right? So they're good, but only in kind of moderation. Because if you do too much of them or they're too high, like the intensity is going to overwhelm the excitement there. Also, the excitement's capped, right? Like if you have more than 9 drops, you don't get any more excitement benefit. Okay, time to build an algorithm, right? And this is the part where I realized that there's a lot more to just excitement and intensity to like actually having a computer-generated coaster. So the track needs to be a complete circuit, right? Which is not trivial. So here's an experiment where these people are, crashing. And here's another one, and it's great because everyone goes on YouTube and thinks they're like really, really clever by like making these like tracks where like cars are crashing into people and all this stuff. And there's really bad music in all of them, and it's all from the early 2000s, which is really fun. So you can go on YouTube and find a bunch of these maybe in your lunch break. Track can't collide with itself, right? Like you can't just build something that intersects with itself. This is something that is really easy when you're building the coaster. You just can't do it. But if you're generating it from a computer, it's going to be tricky to do that, right? Especially if you're kind of like generating a complete track and sort of going as you go. The track, you have to obey the laws of physics, right? You can't, the car has to make it all the way around the track. It has to have a positive speed the whole way that it's going. So how do you build an algorithm? This is a search problem, right? We're searching, there's some large number of possible roller coasters that can be built, and we're trying to search for good ones, right? Like in that sort of space. I chose genetic algorithms for this, mostly because I was excited about it, because I read some Wired article when I was 12, and also because I knew it was kind of useful for protein folding, or at least I'd heard that, so I thought it would be, I thought it was kind of analogous if you're like twisting tracks around and like trying to make them fit in a thing. So if you have 100 track pieces in an average coaster, there are 13 possible track pieces that can be built for the average track piece, right? Like if you have a straight piece, you can go up, you can go down, you can go left, you can right, like 13 average possible of those. You multiply those out, it's roughly 1 billion times easier than chess. And chess is hard, so this isn't an easy problem. This is a really hard problem in terms of the search space, right? So you try to do anything you can to limit the search space, right? Let's remove diagonals, let's remove breaks, let's remove all the other crazy coaster modes, right? Like, let's do this dumbest possible thing and try to get a coaster up and running. Genetic algorithm. There are 3 steps to a genetic algorithm: selection, mutation, and crossover. This is the canonical example, is like a string. You have to express your problem as like a one-dimensional string, right? Or like DNA or some kind of one-dimensional thing. And then what you do is you kind of like swap the pieces and you mutate the pieces, and then you evaluate how fit they are, right? So let's say our goal is the string hello, right? Like, we want to generate this string. We start with a bunch of random strings, right? And this is kind of different than typical search problems in that we generate a pool. We generate like a lot of random examples, and then we kind of like cross them over and like compare the good ones and try to use the good ones more often and mutate our way to a solution. For each of those random strings, we're going to evaluate the fitness, right? So we need a fitness function, which is like a way of evaluating and saying how good is this, right? So the fitness function for a string is just like how many letters would we have to change to get the string hello, right? In this case, the fitness is not very good, right? We'd have to change 5, right? So we'd have to change 5 characters. This is not a good fitness, right? But if we change to this, the fitness is pretty good. It's 2, right? We only have to change 2 characters. The fitness is better, right? So this is how we can sort of evaluate progress as we go. Smaller distance from a good solution is better fitness, right? It's easy. See that? The fitness function is normally the most expensive part. This is kind of surprising. The actual like selection and mutation are pretty easy. Evaluating fitness is usually the most computationally intensive part. We can look at this for strings. The function you use is called the Levenshtein distance, and it's not just simply searching through the string. You have to like search through it multiple times. It's an example of that. Versus just randomly generating a string, you can just generate the string. Levenshtein, you have to search through it multiple times, right? It's the most expensive part of that algorithm, even though it's a trivial string searching algorithm. So yeah, so we generate a random pool of strings. We evaluate fitness. We let the best ones, quote unquote, reproduce and form the next generation of strings. And then we repeat, right? And then hopefully we get to where we're trying to go, or we get good enough solutions. For Roller Coaster Tycoon, we use track pieces instead of strings. Like the track piece was the base kind of unit. And there's another consideration here, which is like, do you want to have the track pieces be contiguous? Like if you have a sharp down piece, you can't have a sharp up piece. Like they're just not going to fit together. I kind of chose to just make them contiguous, so you couldn't generate a track that was like had these discontinuities in it, instead of say like randomly mutating track pieces and seeing what could come up. The equivalent is like if you have a Q, always put a U after it, right? Like if you're doing like word generation or something, which usually works unless you're playing Scrabble and you have all the cheat words. This is the book. It's by David Goldberg. It's really good. You can find it at your library. A lot of good solutions. A lot of example algorithms, a lot of ideas for how to set your parameters, like what percent you should set for mutation rates and that kind of thing. Selection. So this is how we select members from the pool to get reproduced. Basically, the more fit you are, the better chance you have. We kind of make a weighted roulette wheel and then spin the roulette wheel to pick members. So the more fit you are, the more chances you have of getting selected in the next round. Mutation. So yeah, we mutate the string. How am I doing on time, Matt? Oh God. Okay, thanks. Yeah, mutation. So like if we spin a random weighted dice wheel and it comes up with a really low value, mutate the track piece, right? Just change it to some other track piece, right? And then see what happens in the string. Crossover. Some algorithms skip mutation, right? There's benefits about its value. You have to tweak it and see what actually happens, right? So you kind of check this out. Crossover is like the typical DNA. You probably studied this in biology class. You splice 2 tracks, right? And then you kind of combine part 1 from track A and part 2 from track B and form 2 children, right? Occasionally you let the parents survive, right? Sometimes you'll generate really bad children. Occasionally you want to just like let the parents stay in. So yeah, it depends on how often you want to do this based on your function and what it looks like. But yeah, you want to just experiment and see what works for you and what sort of generates good looking stuff. Let's see it. Okay, so I have this code. It's up on GitHub. I'll show you a link, experiment. I can show you a link in a second, so I can run make experiment. What this will do is this will start an experiment. It'll mutate a bunch of tracks. So yeah, so now I'm generating iterations and printing out sort of data about this, right? So iteration 0 is 500 members. The best member has this score. The worst one has this score. Here's the median score. And then of the best member, this is the length of the track. This is how many collisions are in the track. Like these are just the really, really basic building blocks of sort of the fitness function. That sort of let me know whether I'm on the right track or not, right? To completion is how close we got to forming a complete circuit with this track piece, right? It's really hard to generate a complete loop if you're just like randomly mutating tracks. So I built in some code to kind of like complete the circuit and see how many track pieces it takes to do that. Use that as a factor in the fitness function. And then here I'm printing out the track pieces. So this is like the most successful one, right? Like in a given iteration. Like this is just the track pieces that got generated for that fitness function, right? So then what I do is plug that into the game and then see how we're doing. All right, so here's a coaster that got generated. I generated this the other day. So this is something that got generated by the thing. The inputs to my fitness function right now are just the most basic, which is like, can it make it all the way around the track? Is the track a complete loop? How close is it to being a complete loop? How long is it? The longer the track, kind of the better it is. And yeah, this is one that I generated, right? Like it is a ride. It resembles a roller coaster, right? You might enjoy riding this, which is neat, right? Like I don't know, it's cool to see this. I wanted you to observe the on-ride photo immediately after leaving the station. Smart decision by the computer in case you're not enjoying yourself on this vomit comet of a roller coaster. Get the photo in early so you know people are still having a good time. Anyway, consider this when you're building coasters on your own. The wisdom of the computer, as it was. This is another track that got generated. Yeah, I mean, not something that I would build from scratch, but it is like a coaster. It resembles a roller coaster that you could ride, which is cool, right? You know, and we can keep tweaking this and keep sort of generating it and build better and better fitness functions as we go. So yeah, so the problem is I built out this whole thing for like downloading the track into TD6 and like encoding it and loading it into the game and sort of like browsing through experiments and everything. The game is sort of constraining in that if there are any collisions or any sort of like invalid track pieces, it just won't load. So you kind of have to like build it from scratch and like see how it's doing. I'd like to like automate that in some way, but it's kind of tricky for the moment. Right now we just kind of like print out the track pieces and try to build them and see how they're doing in the game and what they kind of look like, right? And how close they are to being complete loops. So yeah, so that's basically it. What I learned from doing this, right? So data inconsistencies will kill you, especially when you're doing anything like really complicated. Like you have to get the building blocks like perfectly right. For a while, like left turns were not generating like any left movement at all. And that really like effed all the later track generation, as you can imagine, when it was like, yeah, this is a complete loop, and it totally just like way off to the right. So you have to get the basic building blocks right before you can go onto this level. So you have to write tests, right? Like this is really, really useful for me, especially with like 2D track generation. I'm just not good at thinking about that. So I just like write a ton of tests. Like anytime I came up with an inconsistency, I just add a new test, right? And so in Go, table-driven tests are really useful for this, right? So what you do is you have a bunch of test cases. You call a function for each of your test cases, and then you check it against the expected output, right? So in this case, I'm calling compatible, right? I'm checking whether two track pieces are compatible with each other. Then if it's not the expected value, right, like true or false, I print out some output about it, right? Then what I can do is, as I get a new test case, I can just load it into this array and just keep adding more and more entries into that array. And so now I have more test cases I can check for regressions in my code. Inconsistencies will kill you, right? Test for 2D code. Fitness function complexity is hard to predict. Like, it was hard knowing going in how complex this fitness function would have to be and how much sort of work I'd have to do to get that sort of working. I have examples. You can go browse the code, which I'll show you at the end of the slide. Make the problem as small as possible, right? So like anything that's complex or hard, like loops, just take them out, right? Like get this dumbest possible thing working, like the smallest possible thing working, because a lot of times you're competing like against yourself, right? Like you want to make sure you stay interested in the project, especially for a project like this where you're doing it on vacation or in your spare time, like you want to keep it fun. So like do really the dumbest possible thing and it'll probably work. And then replace it as you need to, right? Like if something's slow, like figure out, yeah, okay, maybe I can do this in threads or whatever. But yeah, do the dumbest possible thing and then kind of get it going. Future stuff, yeah. So actually plugging in excitement, intensity, and nausea, right? Possibly like the cost. So right now I sort of add penalties, right? Like for collisions and penalties for like not track completes, right? But these are just hard-coded numbers in my code. You could tweak those with a genetic algorithm as well, right? Like you could see like which ones actually give you better functions or not, right? And mutate those parameters based on a genetic algorithm. The other thing is now that we're in C, we can actually call into C from Go. There's this cool library called CGo, or function or feature of the Go language. But yeah, so that would be pretty neat. And it would probably sort of like improve the accuracy, right? Like you can use the really complicated excitement rating without having to redo it all yourself. Thanks Kyle Conroy, who also used to work at Twilio, was on vacation with me and gave me a lot of useful insight and feedback as I was kind of building this project out. And that is it. This is links to the code, github.com, Kevin Burke, RCT. This is my website, link to slides at the bottom. I'm happy to take questions, but I think we have to go out into the hallway to go do it.
Thank you, Kevin.